the workshop for today, and we will speak about the sustainable drainage for food production. And at first, we look on these needs for drainage and its impact. And Minna Mäkelä from Finnish Field Drainage Association, who I also represent. I'm Helena Eija from the Finnish Field Drainage Association, and I will be the moderator today. But now, Minna Mäkelä, you can share your screen, please.
My name is Minna Mäkelä. I'm with the Finnish Field Drainage Association. And this morning I will start our seminar by talking about the need for drainage and its impact, both agronomical and environmental, as well as mention briefly some measures in drainage with environmental benefit. See if I can get it going. So first, some challenges in agriculture of Northern Europe. First of all, we have a short growing season. And in the spring,
вегетационный период. Весной очень много талой воды. Летом распространение осадков неравномерное во время.
And this is only likely to increase through climate change. In the future, there also may be an increase in need for irrigation, and the variation in moisture conditions within the growing season is likely to increase. This past growing season is a good example of a wide variation in hydrological conditions, at least in Finland. Also, our fields tend to be quite level, and a lot of our fields have poor hydraulic conductivity. We have an abundance of clay and peat soils, and only approximately 15% of Finnish fields can be cultivated without any artificial drainage. For the most part, we rely on drainage to have our agriculture going. The purpose of drainage is simply to direct excess water away from the fields. This is done both to create good growing conditions and also to ensure bearing capacity for agricultural machinery. And drainage affects obviously groundwater level down to the drainage depth. Also soil water movement, allowing water to filter down the soil profile. The amount of discharge may not change that dramatically, but the surface runoff will be diminished and drain discharge increased if the drainage is functioning properly. The quality of discharge is improved because more is retained in the soil profile. Gas exchange is improved through increased air-filled pore space, and the soil is warmer and the frost melts faster because the soil is drier. And soil structure is improved because it's not compacted by agriculture and machinery, but also because of the improved water balance. And here is an animation on the basic function of drainage, of subsurface drainage pipes. So water coming from above is filtered through the soil profile and passes through to the groundwater. When the groundwater level rises above the drainage depth, that's when discharge begins. The groundwater level will practically continue rising above drainage depth despite the drainage pipes. When the water level rises faster than the drainage can accommodate, but then it will lower again much faster than it would without the pipes. And the importance of the drain excavation, which is done at the installation stage, is that it's usually backfilled with soil and a little bit of gravel. And the importance of that is even more important if the soil has poor hydraulic conductivity, because the water can then filter through the excavation if it has trouble infiltrating throughout the soil profile. Field drainage can be considered as having two parts. It has local drainage within the field, often subsurface drainage, and basic drainage leading water away from the fields, primarily in open ditches. And local drainage cannot function without basic drainage to lead the water away. And then for the agricultural benefits of drainage, in a well-drained field, yields are increased, as shown by some results from a project called PERA, which I will show also later. Field work can be organized more efficiently, and the usable growing season is longer. And very often, if a field has uneven growth, the problem lies in uneven moisture conditions. Input efficiency is both an agronomic benefit with decreased cost per amount of yield, and an environmental one with less nutrients going to waste. Drainage maintains good soil structure, and well-structured soil can maintain multiple ecosystem services with both agronomic and environmental benefits, such as earthworms, which further improve soil structure, efficient nutrient retention, and deep root growth, which has the potential to increase soil organic matter content. So we have established that drainage is necessary to maintain agriculture, but is it possible to gain environmental benefit from the proper design and application of drainage measures? Well, in the case of nutrient leaching, to prevent nutrient leaching and erosion, all drainage measures should be carefully designed to suit each situation, including soil type and slope and such as. And the design should include drain depth and spacing to accommodate the amount of discharge and to minimize surface runoff. And also the design for basic drainage is something where environmental matters can be taken into account. There is typically a temporary increase in leaching after drainage work as a result of disturbing the soil. This can be minimized by timing the work to as dry a period as possible, and this also decreases the risk of compaction due to the work itself. When a field is well drained, it can support a larger yield, resulting in a much smaller nutrient balances. As a result, much less nutrients are left in the soil susceptible to leaching. This has by far the greatest potential to decrease nutrient load into the ecosystem. If the nutrient cycle within the agroecosystem is inefficient, any attempt to decrease the load later will have smaller impact. There is also evidence of poorer phosphorus availability on poorly drained soils from a current research project that we are engaged in, but the results are not quite ready yet. In addition to this, erosion is also decreased through decreased surface runoff. Efficient drainage throughout the drainage network decreases flood risk, which also decreases risk of erosion, as well as surface siltation. Controlled drainage is a method where water can be retained in the soil by damming devices in wells in the field. This and sub-irrigation can be employed to regulate the discharge and dilute or avoid peaks in leaching. We will hear more about nature-based methods in main channels from Dr. Cadastre today. Functioning drainage and other good agronomic practices in the field are key factors in reducing leaching. In addition, there are other measures developed in drainage, typically involving adding a treatment to the soil or filtering the discharge water at the outlet through various treatments. These include promising treatments, but so far they tend to have lower cost effectiveness because they are usually not quite long lasting measures and their application should be in proportion to the load. So it ends up that there need to be quite a lot of the treatment to have a serious impact on the load. Acid sulfate soils are somewhat of a special case, but they are relevant in Finland and at least in Sweden as well. They contain sulfides in their anoxic reduced state subsoil, which when oxidized release sulfuric acid and trace metals that become soluble under the acidic conditions. This can be associated with agricultural drainage when lowering the groundwater level fast allows fast oxidation. This can be mitigated with controlled drainage and sub-irrigation, which allows to adjust the drainage depth, lowering it only when necessary and keeping it as high as possible for most of the time. In addition, there has been research into introducing neutralizing agents into the subsoil via the drainage network with sub-irrigation. This measure seems to have the same limitation of short duration and proportion to the acidity and hasn't been widely adopted yet. Increasing greenhouse gas emission as a result of agricultural drainage on organic soils is a well-recognized phenomenon. Drainage improves conditions for soil microbiota, increasing soil respiration and carbon dioxide emission. Controlled drainage can be adopted and sub-irrigation to mitigate this as well, along with dams in main channels. In local drainage, converting from open ditches to subsurface drainage can cause loss of habitat and pose a risk for biodiversity. And there are still some open ditches in use in Finland. This can be mitigated by landscape design outside the field plots, but reconstruction of main channels in basic drainage holds more opportunities for adopting nature-based methods than the local drainage. So to end, I will quickly tell you about PERA project. It was a research project where the Finnish Field Drainage Association participated. It was in 2017 to 2020, and it was a research project aiming to find out whether a functioning drainage can produce real agronomic or environmental benefit. And the relationship between drainage, yield, and nutrient balance was investigated with a large pool of data collected from statistic and administrative datasets and questionnaire filled by the farmers as part of their subsidy application process. The questionnaire included question on the farmers' own assessment on how their drainage was functioning. And this whole dataset was investigated with statistical methods to find connections between these factors. So in this table, there is an example of a summary of the results from PERA. In this table, there are yields of barley arranged by yield categories. So the highest category is the lowest yield, less than 3 tons per hectare, and it progresses to 6.5 tons per hectare or more. And this is the N is number of observation, And then there is nitrogen fertilization, and it shows an increase, but not a tremendous increase in the amount of fertilizer added to the higher yielding plots. So there is a nitrogen response in the yield. The next is phosphorus fertilizer, and it shows that it's very similar across all yield categories. And the nutrient balances, the nitrogen and phosphorus balances, by those here we mean simply the difference between applied nutrient and the nutrient recovered as a yield. So here we can see a clear connection between higher yield and lower nutrient balance. It's evident on both nitrogen and phosphorus, with a significantly larger proportion of applied nutrients recovered with the yield when the yield was better. This indicates a growth factor other than plant nutrition to have been limiting in the poorer fields. And this shows not only higher input efficiency, but also lower leaching risk on better yielding fields. And also there's a trend visible for higher proportion of fields with subsurface drainage in the higher yielding categories, and also a trend towards lower proportion of rented fields in the higher yielding categories. And this figure shows the relationship between yield and weather, with the relative rainfall of June in the x-axis. So the y-axis is the yield of barley. It's against the same example of barley. And the relative rainfall means that one means the average rainfall that is typical in Finland. 0.5 means half the rainfall, and 2 means double the rainfall from typical. And it shows a clear difference in response on different drainage categories on water stress. So fields where drainage was good, which is indicated in blue here with the blue dots and the blue trend line, the yield of barley remained the same in wet and dry years. But the drainage was poor, which is the yellow trend line and yellow dots. The yield of barley decreased in wet years. And on fields with excellent drainage, which is here shown as green trend line and green dots, the yield increased with increasing wetness, showing that the plants were able to benefit from the added moisture instead of suffering from it. And this shows not only a response in the amount of yield to good drainage, but also that good drainage can improve the resilience of the agroecosystem to unusual weather. And then, as a quick summary of results from PERA project, a functioning drainage can enhance productivity while decreasing nutrient balance. The difference in drainage status is most visible under stress conditions. And functioning drainage makes it possible to adjust fertilizer levels to meet yield potential while nutrient balance remains low, increasing input efficiency and decreasing risk of leaching. So that was my short contribution to the seminar, and I believe there is a short time for questions here.
Yes, thank you, Minna, for a nice presentation. Yes, we have time for questions. So please go on if somebody want to ask question.
Maybe I can ask a question. Wendelin Wichtmann, my name, from the Greifswald-Meyer Center and the Desire project. Thank you very much for this presentation. Very nice pictures and very nice outcomes. But what I would like to say is that there must be a stronger distinguishing between peatland organic salts and mineral salts. So for peatlands, drainage is something like poison. You lose every year 1 to 2 centimeters of height of your field, and you produce 30 to 60 tons CO2 per hectare and year. And it turned out in different investigations in Netherlands and in Germany that subsurface irrigation does not significantly lower the greenhouse gas and the nutrients emissions. So please distinguish organic salts and mineral salts. Otherwise, we produce very high export of greenhouse gases and nutrients from the fields. Thank you very much.
Thank you for the comment. Yes, it's a very big problem this week with the greenhouse gas losses from the peatlands, and we are discussing it a lot, of course, in Finland, what to do with that thing. So, but I think we are going on now, and then we can discuss more about that in the end of the seminar. So then we can go on, and next we will hear about two-stage channels for environmental preferable drainage by Dr. Kaisa Västilä from the Aalto University in Finland. Please, Kaisa, you can share your screen.
Yes. Okay, so hello everybody. I'm Kaisa Västilä and I'm affiliated with both Aalto University and the Finnish Environment Institute in Finland, and I will be talking mainly about two-stage channels for environmentally preferable drainage, but also some other methods that there are to take into account better the environment when we are doing the main drainage, so meaning the open ditches. So we have heard in the already in the other presentations that there are some problems and challenges that we have in our agricultural streams, and they are related both to the ecology and to the technical functioning. So we know that the ecological status of these channels is in large parts only poor or moderate. So humans have modified a lot the natural streams and brooks for the purpose of the drainage, which is necessary in our climate conditions. But this has caused some ecological problems, losses of habitats and increased nutrient transport as well. But there are also technical issues. So these ditches are often growing with vegetation, siltation, so they lose the conveyance capacity quite much. So the technical challenges are also there, and with the climate change there are also new things that we need to take into account, like the need for water storage and irrigation perhaps. So I think with this background we should also twist our minds in a new mindset. How can we solve these problems now in this century? And I put here some photos. If we try to improve the ecological status and the functioning of these drainage systems, of course we need to look how things are in the nature. I fully understand that we cannot go back to the natural state, that everybody understands that there are these constraints by the land use and by the agricultural requirements, and also of course money is an issue. We cannot restore everything back to some ideal state that was there some hundreds of years ago, but we should look how these natural channels look like, what features are there that we can use in our engineered channels to bring back some of the nature and some of these good processes that are taking place there. So when maintaining our ditches, we should think about the planform of the ditches, so avoid straightening and allow perhaps some small-scale meandering there. We should think about the cross-sectional and longitudinal variation in the channel morphology, in the channel width and depth. In nature, nothing is like homogeneous for long reaches, but the streams are really variable. We should think about the slope stability. And of course, if you look in his pictures, you see a lot of vegetation there. So both aquatic, but mainly riparian vegetation. So this also comes to the maintenance, how we maintain these ditches and do we allow vegetation there. You see that the bed materials are really variable in these channels. So large materials, stones, gravel, everything down to the clay. And by the way, in this presentation, I'm mostly really now talking about mineral soils. So these methods are suitable for mineral soils, and I'm not dealing with organic or peat soils here. And we can also restore back some of these habitats that have been lost. So keep this in mind when designing the drainage maintenance. And so how we can bring some of these features into our channels. So we call these nature-based solutions. So they use the natural functions and features of the ecosystem, and they put them into the engineered context. So in our case, we are talking about the agricultural channels. So some of these things that we can do are at different levels. So at the catchment scale, we can restore some of the mires or peatlands to cut some of the highest discharges. We can have some constructed wetlands, as you see at the bottom left, the one of the best functioning and most monitored wetland in Finland, Ovi. And these can have some water quality and wildlife benefits, and also can retain water. If we have problems with erosion, such as you see here on the banks in this channel, we can put some sow grasses or put some fascines, different types of also erosion protection made of vegetation or erosion control blankets. Of course, we can then use some stone materials, but now I'm mostly talking about these nature-based solutions. So I want to mention the vegetation. Vegetation is actually very good against erosion. We can also have some natural like bottom ramps or rocky sills, as you see in this middle photo here. So they work for erosion protection, but also they work for raising the low water levels, and they can diversify the habitats a bit. We can do some habitat restoration. For instance, there are cases where spawning gravels have been restored in fully agricultural surroundings. And there are examples where trout are living in these agricultural areas, and they can benefit from this habitat restoration. And what I'm mostly focusing today are these two-stage channels. You see a photo here. So they can really enhance the drainage and flood mitigation and also bring some environmental benefits. So here, what is meant with two-stage channels? So they are considered now as a new environmentally preferable alternative to the conventional dredging and maintenance of agricultural ditches. So in the conventionally dredged channel, typically when we do the maintenance, we excavate from both banks, and then the channel becomes typically more wide than in the natural stage. So these channels are quite wide from the bed. And the idea with this two-stage channel is that we don't change the width of the existing main channel, but rather we excavate a floodplain on either one side of the existing channel or on both sides of the channel. And the floodplain should be at about the mean water level, so that it will be inundated for something like 2 to 4 months.
и заполняется от 2 до 4 месяцев в году в зависимости от осадков. Вот это
floodplain on one side of the channel. And the idea here is that in the two-stage channels, we have a narrower main channel. So what happens in these conventionally dredged channels often is that when we have low flows or mean flows, the water depth is really quite small in these channels. So meaning that also the flow velocity is quite small, and there can be deposition and siltation and vegetation growth in this channel bed, as you have seen in the photos that I showed. It's really typical. In this two-stage channel, the idea is that the narrower main channel will keep higher flow velocities also during low flows. And in this, the idea is that it will prevent or minimize the siltation, the deposition of sediment in the channel bed. There is also controlled vegetation growth. So we want to have vegetation on the floodplains and banks, but the idea here is that we try to keep the main channel clear of the vegetation, or we hope that this would work in that way, that the channel would itself keep clear of aquatic vegetation. But the floodplain vegetation, and we have also this large geochemically active surface area in two-stage channels, so meaning that we have a lot of contact area between the channel boundary and the water here on the floodplain. So this will benefit the water purification processes. And we also have increased hydraulic retention. So we can actually reduce the flood water levels with this design, but still have higher water retention because we have higher cross-sectional area in the channels. Discharge can be conveyed, or even some of the discharge can be permanently stored on the floodplain, but still the flood water levels are reduced. Some photos from Finland. So we have about 20 of these channels. They are really short stretches, only 100 to a couple of meters. But in some cases, we have perhaps 5 sites where we have approximately 1 kilometer length of the two-stage channel. So you see in these photos channels after different time since they were constructed. So since the floodplain was excavated, in some cases there are still bare banks 2 years after construction. Here you see a very nice example after the vegetation has established itself. Here is one recent example where this was photographed 4 months after the floodplain excavation. You see the main channel here, and then the floodplain is also already starting to get vegetated. So we have, with many colleagues, reviewed the performance of such two-stage channels in the agricultural context. And in this open access article, so everybody can access this article. Here is the link to there. And there we show also some case study examples on two-stage channels. So this is mainly based on the research that we have been conducting in Finland and what has been conducted in United States, where these two-stage channels are already kind of the best management practice in several like Midwestern states. And it's also knowledge about what happens in these kind of channels when they are kind of in the urban context. But there they have been more designed just for the kind of stability and for the flood reduction. But what is new, what is kind of the new thing is that we are also thinking about the nutrient and suspended sediment removal potential of these channels and also the ecological benefits. So what I'm showing next are several findings that are reported in this article. So you can check the article. But the main benefits of these two-stage channels in comparison to conventional maintenance dredging are based on our literature review, that we have longer term functioning of the drainage because this low flow channel can keep itself clean. So it has effective self-cleansing capacity. There's also the retention of suspended sediment and phosphorus on the floodplain, as well as denitrification, so removal of nitrogen on the floodplain. So this likely enhances the water quality. There is larger plant and fish biodiversity, and there can be more habitat for pollinators. The main channel geometry is more natural-like, so meaning it is this more narrow and there are these faster flows than in the conventional dredging. And these natural-like flow conditions also allow habitat restoration. And so this can link back to the larger fish biodiversity. Other taxa, such as macroinvertebrates, may benefit from the improved connectivity between the main channel and floodplain, and also from the more diverse vegetation. And we think that there are also some landscape and recreational benefits because the landscapes become more varied. But there is a disclaimer here. So there are very limited studies on the biodiversity impacts and on the medium to long-term physicochemical performance. So what I say about the larger plant and fish biodiversity is only based on 2 or 3 or 4 papers. So it is very limited studies that are available. And for instance, there are only few works that provide an experimentally obtained over annual scale mass balance for suspended sediment or nutrients. And the processes in the low flow channels are not well taken into account. So there has been quite much studies about the floodplain processes, but we also need to think what happens in the main channel. But I can summarize this that it looks there is potential with this 2-stage channel approach and some positive impacts. I now show a bit what this means in practice based on research at one site in Finland, so Ritobecken Brook, where a 2-stage channel was constructed almost 12 years ago. It's clay to silty soil, and it's a small 10 square kilometer catchment, and the mean discharge is about 120 liters per second. And before excavation of the floodplain, it looked like this. So a narrow channel with some very small meandering there. It had been conventionally dredged, of course, in the past, some tens of years ago, but it had lost its conveyance capacity. And so the fields were often flooded also during summer conditions. So this was, of course, very bad for the agricultural productivity. So then a 2-stage channel was excavated there. And we have been monitoring the site actually even before the excavation. And here we show what happens in the channel. So we have monitored the geometry of the channel. So here you see the main channel, and then you see the even about 5 meter wide floodplain. So we have 9 years of record of how the channel forms itself. And we can really see here that there is no deposition, there is no siltation in the main channel bed. Rather, we see actually that the old deposits that have been collected there after the conventional dredging some tens of years ago have been flushed away. So the self-cleansing capacity is very good. So there is no siltation in the bed of the channel. And this is only a one cross section, but the same pattern repeats itself across this monitored reach. So this is representative of what happens in the entire reach. We also see that there is some deposition on the floodplain and on the excavated bank. So this 2-stage channel design maintained the drainage depth and also the sufficient conveyance capacity. And this decrease in the bed siltation can support also stream biodiversity. But we will continue the monitoring to see if it's what happens there in the future. We have also calculated the suspended sediment and phosphorus mass balance, and there was significant retention of suspended sediment and phosphorus of the order of 15% if you have 1 kilometer of this two-stage channel. But however, because there was flushing of the old deposits in the low flow channel, actually the total net retention is much lower, because the main channel processes kind of course decrease the impact of what happens on the floodplain. But the retention can be likely higher if subsurface drains discharge on the floodplain. This was not the case in this site, and if the vegetation is maintained. So we are conducting further investigations on these issues. I also show here some preliminary results from plant species richness at the same two-stage channel. And there we see that in conventionally dredged reference reaches, the number of plant species was notably lower than in the two-stage channel. So this right-hand side column summarizes all the plant species on the floodplain and the bank of the two-stage channel. So the column is much higher than what are 3 conventionally dredged reference channels. So there are many species shown by this yellow to orange color that are unique to these two-stage channels. So the two-stage channel really kind of increased the plant diversity. And this can then be positively reflected also on other taxa. But this is only one site, so we have to, of course, be careful when interpreting this, but it looks good. There is also wider potential of this two-stage channel design, because we believe that it works better than these kind of edge of field buffers. The floodplain can treat both the lateral runoff, but also the loading from the upstream areas. And these buffers on the edge of field cannot treat these upstream areas. So they only treat what comes locally from the fields. And we also see that perhaps the plant biodiversity can be improved in comparison to the edge of field buffers. I have collected here some cost factors. I realize the time is running. Try to wrap up this, but the costs of two-stage channels are pretty much higher than for the conventional dredging. So overall, the construction cost ratio is about 4. So two-stage channels cost 4 times more to construct. There is some land lost during the construction because these are wider than conventionally dredged channels. So we have then computed kind of the total costs, but also evaluated the monetary environmental benefits of two-stage channel design. And this has been conducted for a 60-year period. So two-stage channel in comparison to conventional dredging. And here we selected a site which has significant environmental value already. So this site, Verniönjoki River in Finland, has these Uniocrassus mussels, so protected mussels. So we see here when we compare the costs that the two-stage channels have large initial construction cost, but actually they have much lower maintenance cost compared to the conventional dredging based on our estimates. There are also significant costs related to lost field area because two-stage channels are not integrated into the agricultural subsidy system at the EU level. So what is required is still that we have 3 meters of buffer strip, even though we have floodplain. So we still need kind of this double things in there. And this, of course, leads into the lost crop value because it cannot be cultivated because there needs to be this additional buffer strip. And this is according to the present subsidy scheme. But we see that there are notable environmental values for both for phosphorus retention and for the preservation of these endangered species. And if we sum up the costs and the environmental value, we see that the environmental benefits are much larger than the costs of the two-stage channel, in this case at least, whereas the conventional dredging in this case led to negative, so meaning that there were costs. I also have a preliminary decision support tree for the optimal kind of positioning of these channels, but I don't have time to go for that now. I can just say that the design is widely applicable to small and medium-sized ditches and from different mineral soils, from clay to sand soils, and especially favorable if you have high biodiversity values in the channel, or if you have unstable conventional channels, or they require frequent clean outs. And with climate change, I think there is more need for such solutions. So I end up with this slide showing some of the benefits, and also we have proposed that the floodplain should be integrated into the CAP, in the EU subsidy system, as kind of an afterfield vegetated buffer, so that it could replace the edge of field buffer strip, which you see here. Thank you very much.
Thank you, Kaisa, for your nice presentation. And now, if somebody have something to ask, so we can ask one question, and then we can take a little break after that.
Yes, please. I have some questions. Anushka here from Sweden, and I have been following one of the two-stage ditches which were constructed in Östergötland County during 2014. And it's very nice to hear your presentation and see that you still believe in stable terraces and channels and self-maintaining low-flow channels, because our experience is that both the meandering and the terraces have unfortunately eroded. So I want to ask you about your good advice to get stable terraces and stable self-sustaining low-flow channels.
Thank you very much. Very, very interesting. I think for the terrace or the floodplain, so at this site, we showed vegetation there already in the first, so straight after the excavation. So I think this is what is my idea why this is working. So the vegetation will prevent the erosion and increase or lead to some deposition. So I don't know how the vegetation is at your sites on the floodplain.
There has been sowing of vegetation, exactly as you say, directly after construction. But because it's heavy clay soil, it was very difficult to establish the vegetation. So it needed at least 3 times of thawing under the following years, and still the vegetation is not really established after 6 or 7 years.
So
and
this must
problem is that there is more vegetation in the low flow channel than on the terraces. So the water is looking for a new flow channel on the terraces and thereby eroding.
Okay, yes. So it must be the soil, some kind of soil type effect there, I think. But so it should be then based on this, and it's very interesting to hear that somehow these should be then also the soil type taken into account, so that we can have vegetation on these terraces. Because as you say, if there is no vegetation and we have the high flows, then there will be erosion. But about the main channel, so what I also showed is that we have some loss of the material from the main channel, as I showed
Yes,
So believe this is mostly related to the old deposits that have been flushed away. But now we are continuing the monitoring. So in a few years we'll go back and measure exactly the same spots and see, because if this still increases that kind of the main channel depth, so then we start to be scared that there is actually some erosion of these kind of virgin materials in the bed soil. But is this the same that you are also observing?
We have both
or the opposite?
erosion areas in the low flow channel, but also deposit areas, especially on the areas where there is a lot of vegetation.
Yes.
Because during 2018, when it was a very dry summer, there was no chance for vegetation on the terraces to grow, but in the low flow channel there was moisture. So a lot of vegetation established there, and they act as a filter then and catch up all the sediment in the low flow channel. So the low flow channel shows both sedimentation and erosion, and the terraces show mostly erosion. So kind of, so far as I can see this experiment, it's not really successful here, but it's nice to hear that you have succeeded in Finland.
Yeah, this is very interesting to hear, and I think I will contact you also for more details and perhaps to see your results. But exactly the key is the vegetation. So where do you have the vegetation? So there you will have a deposition and prevention of erosion, and I think it comes a lot also to the channel design, but of course it's also the hydrological year. So if you have very dry conditions and difficulties for the vegetation to establish on the floodplain, then you can start to have these things. But thank you, Anushka, very much, and I think I will contact you for some more detail and discussion. Welcome. Thank you.
Goodbye.
Thank you. And we have also some questions in the chat, but I think we take now 5 minutes break and leave the chat questions to. If Kaisa, you have time, you can.
Yes.
Or
sure.
Then we can send done in the general discussions. But now we take a 5 minutes break. See you. The next we will hear about the recent and ongoing activities in renovation and the construction of drainage systems in Latvia. By Dr. Ainis Richness from Latvia University of Life Sciences and Technologies. Please, Ainis, go on.
Okay, thank you, Helena. Good morning, everyone. Yes, today I will talk about recent and ongoing activities related to subsurface drainage and main drainage in Latvia. And this presentation is part of WaterDrive Work Package 3, which is entitled Advancing New Technology and Methods. And the content of my presentation will be as follows. So in the beginning, I will talk about detailed mapping of subsurface and main drainage systems that we have in Latvia and provide some examples how we are using this type of information and what are advantages and maybe further improvements to be done for this detailed mapping system. And then I will provide applications of not only this drainage information system, but also other geospatial data in planning process for implementation of measures for water quality improvements and also for water quantity at some point. And then the results of monitoring activities also will be presented because I would like to emphasize that not everywhere any of these measures will work. We heard also the examples from previous studies and from previous presentations today that two-stage ditches might work excellent, for example, in Finland, but they might struggle, for example, at some circumstances in Sweden. So I'm turning to the information system of drainage Cadastre, as we call it in Latvian. And here you can see how it looks like in the web application, in the web version that you can use in any browser. And this system is produced and maintained by the state limited liability company, Real Estates of Ministry of Agriculture. And in time, this system has been improved, and more comprehensive background maps included in this drainage cadastre system. And this adds additional benefits to see how it looks like from different perspectives. From, for example, we have this OpenStreetMap, orthophoto maps, which are updated again constantly. Then infrared map, digital elevation model derived from LiDAR with a very nice resolution. And then we also have slopes with contour lines, which also has some functionality that can be used in this system. So when I go closer in the scale, you can see that these lines, which represent water courses in Latvia, are divided into mainly two categories. And here you can see that these red dotted streams are...
Вот эти вот красным пунктиром, это то, что национальное значение имеет. Есть определенные критерии.
And the catchment area should be more than 10 square kilometers. But then also you can notice in this screenshot that there are some also rather large streams which are without any dots. So this indicates that some stretches of some rivers or even entire river can be natural. And by this I mean that these streams have never been artificially created or maintained or straightened as it was in the times of creating agricultural drainage systems. So in these terms also the difference is that this Real Estate of Ministry of Agriculture can maintain these streams of national significance, but when we have these stretches or full rivers with natural conditions, so those are left as it is, and no additional works can be done over there by this unit. So when we go closer, you can see more detailed information about the also subsurface drainage. So again, here you can see one stream which is of national significance, and then on the right side open ditch, which is not classified under this category because it's likely that it has smaller catchment area. And also you can see that the pipe connections, surface runoff inlets, and catchment areas of a single subsurface drainage system, and also for these streams of national significance. And where the subsurface drainage does not appear, so then these areas were digitized by using digital elevation model to find the border between two adjacent catchment areas. And so for this information system, we have available web version. You can see the web address also for this site, and this system, as I told before, is elaborated and maintained by the state limited liability company, Real Estates of Ministry of Agriculture. Also, we have a smartphone application which adds a very nice functioning of geolocation. And this system is created and operated by a joint stock company, Latvia's State Forests. And in this website, which is also available below, you can see many more layers which are available under this smartphone application and also in the web version. And what is very useful that there are some of layers of as shape files and also as geodatabases that can be downloaded from this website. And of course, the geolocation adds much more benefits for the farmers, as they can walk through the field and try to find their drainage systems that usually you cannot see. And then upon request, it might be possible to obtain also separate shapefiles and geodatabases to be used in any kinds of GIS software. And this information again is kept by real estates of Ministry of Agriculture. And how these maps have been created, you might wonder. And here are a few examples, again from my colleague, how these maps have been created. So here is an implementation plan which was available for the most of agricultural lands where drainage systems have been installed during the Soviet Union times. And these implementation plans have been scanned using scanners or plotters, depending on the size, and then these systems have been manually digitized by representatives of real estate of Ministry of Agriculture. You can imagine what the work can be to digitize all the streams and also the subsurface drainage pipes, open ditches, also drain collectors, and so on, and all the other information. And then we used the orthophoto map was used, and then it was digitized and georeferenced in the position as it appears in the nature. So a lot of hours, a lot of effort and funding have been invested to prepare such a nice looking information system for subsurface and also open drainage systems. And this information is being used extensively by our university and by our researchers. First of all, we are creating a simple maps characterizing a specific area. Then we can create catchment area for specific sampling point. Then we can use this data to plan implementation of water management measures. And you can imagine there are many more applications for such a detailed information on drainage systems. And one example that also I would like to explain is, for example, we also might find fields which are with very minor slope and which has different these pipe sizes. And for example, we can using this data look for some fields which are where we can try to install controlled drainage system, because we don't want to use too large collectors, we don't want to use too small ones, we would like to have them somewhere in between. So these are just a few examples. You can just imagine what else we can do with this kind of data. And then how do we apply this geospatial data in the WaterDrive project? And so we are using these subsurface open drainage network maps, land use as Korean land cover, field blocks from Rural Support Service, digital elevation models with a spatial resolution of 2 by 2 meters, and then a soil texture map, which is prepared by and hosted by the Ministry of Agriculture within one project, where similarly to the drainage network, Soviet Union time maps have been scanned and digitized for those agricultural areas where it was possible. And there we have also information on soil texture and other, at some point, other parameters of the soil. And currently we are, another project is implementing where we will try to improve this soil map with additional information, so that we would have as much as detailed the soil map as possible for whole territory of Latvia. So I'm switching to some maps. And here, for example, you can see the open streams, open ditches, drainage collectors, and main streams in the Sveta River Basin, which is a demonstration object in demonstration catchment area in the WaterDrive project. And then using these maps on land uses and digital elevation model, our project partners from Swedish University of Agricultural Sciences elaborated this type of map where you can see where would be the best locations for constructed wetlands. So in this case, also hydrological characteristics of this catchment were utilized for this exercise, also slopes and some other information like roads, road map, and some other maybe aspects which I do not mention now, so that these kind of maps can be created. And here you can see that size of the wetland depends on the contributing area, and as larger contributing area you will have, as larger wetland would need to be constructed to improve water quality from this contributing area. So we are using the knowledge from the WaterDrive project and trying to make next steps in finding best locations for different measures. And here I would like to show a few examples from Live Good Water IP project, where we use a similar manner, but maybe more detailed, for more detailed and more comprehensive analysis, since we have gradually we have improved our abilities in using geospatial data, and therefore we are it is possible for us to move more detailed and more comprehensive analysis in time. And here you can see water sampling sites in Aģe River basin, and there we have 14 water sampling sites where we collect the water samples on a monthly basis, and main tributaries before and after wastewater treatment plants, and then also in open ditches and subsurface drainage systems, just to see what is the background coming out from agricultural areas as well. And then it was quite interesting to see first results. And if you know how water is flowing in the catchment area, so you can create such a schematic representation of multiple sampling points. And basically what you can see that there is one source of pollution that affects quite a long stretch of the water quality in this Aģe River. And with this manner, you can see that there is rather bad conditions in the upstream area, while at the outlet, which is GWAA1 point, you can see that the water quality is become high or good according to water framework directive criteria that we are using in Latvia. So in this way, geospatial data helped us to identify, and also of course water sampling, that we are having a major problem with one meat processing factory which is in the upstream area, which affects, as you can see, also quite a lot of downstream water quality in a rather long stretch. But then also we can see that at some tributaries also we have some water quality problems, and we can start to think what we can do in these areas to improve water quality. And then we used a similar approach as in WaterDrive project, and we were looking not only for best area to make it slightly deeper and create environment similar to constructed wetlands. And here maybe is another example. You can see this is a Mazupīte stream, where again there is a part of field which has been used only for hay. And so these sites could be more easy to discuss with farmers to implement these water management measures to improve water quality. So not only the sites, but also some specific local characteristics that can be used to determine the best location, because it is clear that farmers not always will agree to use their productive land to implement measures, but in the case if it is low-lying area or less productive, then these conversations can be more successful. And so the results of monitoring activities. So here I would like to show you that we have 6 measures that have been implemented in Latvia starting from 2015, when the funding from the Rural Support Service became available for investments in infrastructure development and in agriculture and forestry. And so these 6 measures have been successfully implemented. And just to give you some insight on how much funding was available. So for the streams of national significance, approximately 44 million euros were available, and is still available now, starting from 2015 until 2021. And then when we come to the streams and ditches and subsurface drainage systems, which are owned also co-owned by multiple owners, or by one owner or municipality. So for those landowners and water managers, 53 million euros were available during the same time period. And overall, it makes of investments of almost 97 million euro in reconstruction and renovation of drainage systems in last years. And here you can see 2 sites where we are lucky to monitor in terms of constructed wetlands. So we are having this surface flow constructed wetland receiving water from agricultural fields. Again, you can see how we are using this information system to show from which area this water is received. And then we are having also subsurface flow constructed wetland nearby, which receives water from hard surfaces and storm water from farmyard. And what is important for this surface flow constructed wetland, the catchment and wetland surface area ratio is 0.5%, which is, I would say, quite decent to expect a good removal of nutrients. And then another example and of surface flow constructed wetland with Vīnočviera for hydrological measurements. And then you can see the subsurface flow constructed wetland that also has been presented in one of our previous events by my colleague Linda Greenberger. So here we have water is flowing through the substrate in underground conditions. And this is how it looks like in nature. So we have this pond that where these larger particles can settle down, and then water is pumped in the well, distributing water in the subsurface flow constructed wetland. And then the retention of all parameters monitored is quite impressive to my mind. So as we expected from agricultural fields, we received more nitrate nitrogen, as it is the dominant form in agricultural areas drained by subsurface drainage systems. And then we received rather high concentrations of ammonia and also of phosphate, phosphorus from the hard surfaces and storm water from the farmyard. And overall, I can tell that that these numbers of reduction looks to my mind rather good. especially for subsurface flow constructed wetland, since we are able to reduce phosphorus concentrations for approximately 80% and concentrations of ammonia for 68%. So this shows that these type of wetlands can be used to improve water quality, not only from agricultural fields, but also from the farms and where the livestock is grown. And there are many other options to use constructed wetlands for water quality improvements. Here we have the third wetland we are monitoring. You can see it's slightly different in shape, and in these parts where we have deeper zone in between in the beginning part, and then we have this vegetation part with rough dense vegetation. And this was the outlet structure, but we were able to, in last year, we were able to change this outlet structure so that we would be able to monitor again water flow and also other hydrochemical parameters in water. So this well arrived in Latvia from Finland, and here you can see monitoring equipment which arrived to Latvia from Norway. So we have a rather good collaboration with different institutions in terms of monitoring equipment from different countries. And then what we saw from the monitoring results from 2018 until 2020, that this constructed wetland is not removing any nitrogen and any phosphorus. In fact, it adds something to the water. And here, what I would like to pay your attention to, that we have very low concentrations at the inflow. And basically that shows us that you cannot clean already clean water more. So this brings us back to targeted implementation of these measures, because there might be a chance that at some point at some specific locations constructed wetlands actually are not needed. But what I can tell about this constructed wetland, that it adds a lot of biodiversity component to the area, and we can see birds nesting there, and also we have these different amphibians living there, and obviously waterfowl also is living there almost year round. And so there might be different purposes for constructed wetlands, and in some cases you will not see the nutrient reduction, but you will add other other benefits. And then the last example that I would like to show you is a controlled drainage. One of study sites where you can see there is 19 hectares of free drainage and 25 hectares of controlled drainage, and very simple wells. So we are having the free drainage in this mode, still having some possibilities to measure water flow. And then another well for controlled drainage system. You can see in this picture, again, it is not manufactured in any factory, but it is adapted to for this purpose. And you may pay attention to the fact that this well is completely dry. And this shows that even if we plan to store water, so then water might not arrive in the decent amount or might dry out. The groundwater tables might drop below the drainage system depth, and therefore we are not able to store any water. And in terms of brief results, it again depends from the topography of the site. So we monitor the water level in controlled drainage field in 2 locations in micro depression that you can see with the gray line. And then also with this orange line, so that somewhat upper part of the field. And you can see that even though the elevation difference is rather small in this field, still it has effect on the groundwater level. And in this micro depression, you can see that groundwater may rise approximately 30 centimeters to the ground level, while in the upper part only approximately 1 meter from the soil surface. So overall, this might work in some circumstances, but still for controlled drainage, water is needed to be stored. And if we have rather dry conditions in spring, so there is less possibilities to store water. And so the conclusions I'm having that monitoring activities are very important. And I would like to say that those are foundation for water quality improvements. If we know the current situation, we can think what we could do to improve the situation. And of course, we can use also modeling tools, but those might not provide so detailed information about the existing situation. So then we are having so many geospatial data now, and even more is coming, including land and satellite based, as we discussed in one of our previous workshop. So our task is to use those data wise in water management and try to get most benefit what we can from each data set. And I like what was said by our colleague again from Swedish University of Agricultural Sciences, Omran Al-Shihabi. So doing the right thing in the right place. I'm not sure if he is the original author of this sentence, but I liked it a lot and I continue to use it. And this what we need to do to improve efficiency in both water and nutrient retention, and also from the cost perspective. And then the last one is that the water management will not solve all the problems. So we also need to remember and promote in-field practices. And from this perspective, I again would like to remind you for our principle that is used in nutrient management: right source, right rate, right time, and right place. And only in combination with water management practices and in-field practices, we will be able to reach our water quality goals. And to conclude, you have to learn walking before you're running. And this can be applied also for application of spatial data and also other knowledge, technology, and whatever you can imagine, so that we could improve water management in time. So I can still feel that we are not yet running in full speed in terms of water management, and also in terms of implementation these in-field practices, but we are increasing our walking speed. And I hope that with any next project, we will increase our speed until we will run in full speed. So thank you for your attention.
Thank you, Ainis. And I think we will go on now to the next presentation. You can ask questions to Ainis in the chat, and Ainis can, I think, answer there, and then we can have a short discussion in the end of the seminar. And the next we will then hear about the role of land reclamation in the sustainable development of agriculture in the Kaliningrad region. Please.
Здравствуйте. В Калининградской области мелиорация земель играет очень большое значение. Основная часть осушенных земель
is farmland, and in general This land
для производства различной сельскохозяйственной продукции. В последние годы происходит интенсификация сельскохозяйственного производства. Для этого существует государственная поддержка, направленная на восстановление мелиоративной системы. Осуществляется субсидирование фермеров, сельхозтоваропроизводителей на выполнение различных мелиоративных работ. Ну и, в общем-то, получены достаточно хорошие результаты в связи с этим. Улучшается мелиоративное состояние земель, и это позволяет выполнять различные мероприятия по развитию сельского хозяйства. Ну, что касается комплекса мелиорации земель Калининградской области, то территория области, она находится в зоне избыточного увлажнения, и это требует развития осушения. Ну, что касается доли осушенных земель и осушительных систем, соответственно, то в области находится 23% осушенных земель в целом Российской Федерации и 70% польдерных земель. Ну, что касается польдерных земель, слайд перевести, то они находятся в основном в Славском и Полесском, в Славском и Полесском районе. Ну, что касается Славского района, тут около 70 тысяч гектаров таких земель. Эти земли обладают высоким естественным потенциальным плодородием, и поэтому важно проведение мелиоративных работ на польдерных системах. Здесь достаточно протяженная и частая осушительная сеть, представленная открытыми осушительными каналами, закрытым дренажом, а также насосными станциями, водозащитными дамбами, сооружениями на магистральных. Ну и что касается польдерных систем, то они имеют комплексное назначение. То есть
they have a complex, they serve a complex person. They not only drain land for agricultural purposes, they also provide living conditions for the population, which is rather high. The number of the people living within the podland areas is rather high.
В землях находятся 114 насосных станций, 720 километров дамб, а также 13 565 километров открытых каналов, в которые осуществляется регулирование водного режима, а также 11 909 километров магистральных и проводящих каналов. Это характеристика, вот первые два показателя – это характеристики польдерных систем, а последние показатели, включая закрытый дренаж протяженностью 362 500 километров, это уже характеристика осушительной системы Калининградской области в целом. Ну и как в польдерной, так и в называемой самотечной зоне, в общем, осушительные системы имеют комплексное назначение. Они осушают земли сельхозназначения, земли населенных пунктов, муниципальные земли, земли лесного фонда, объектов инфраструктуры. То есть осушительная сеть, она имеет комплексное назначение. Но она была создана достаточно давно. Первые работы по строительству польдерных систем относятся к XVI веку. Ну и, в общем-то, структура польдерных систем, она, да и в целом области, она сформировалась уже к началу XX века. Ну и что касается наличие осушительной сети, то около 80% территории суши имеет осушительную сеть. То есть площадь мелиорированных земель составляет 1 миллион 500 тысяч километров. То есть нет, 1 миллион 78 тысяч километров. Ну и в общем-то, на территории области достаточно, так же как и на польдерах всей территории, достаточно равномерно распределенная сеть осушительная, представленная закрытым дренажом, в том числе довоенной постройки, реконструированным закрытым дренажом, а также сеть открытых регулирующих, проводящих и магистральных каналов. Но польдерные системы сосредоточены на территории, основная часть на территории Неманской низменности, на территории Курского и Калининградского заливов, а также в поймах рек Прохладной Приголи. Ну и что касается структуры земель, то здесь основная часть земель сельхозназначения. Ну а общая площадь свыше 1 миллиона гектаров. Пожалуйста, следующий. Ну и что касается непосредственно земель сельскохозяйственного назначения, то числится 596 300 гектаров, но в том числе, опять же, есть земли, которые раньше орошались, это 1800 гектаров, но в настоящее время эти растительные системы списаны, земли не орошаются. Ну, а ранее, вот в дореформенный период, площадь таких орошаемых земель составляла 4500 гектаров. Но это связано с тем, что, несмотря на то, что область относится к зоне избыточного увлажнения, в летний период ощущается дефицит влаги, и поэтому есть необходимость полива. Но полив здесь осуществлялся при помощи дождевания в основном. Но кроме того, на польдерах техническая возможность осушительной системы позволяет выполнять их двустороннее регулирование, предупредительное шлюзование. И там тоже были построены, кроме осушительных, оросительные насосные станции, а также сеть для орошения использовались как широкозахватные, так и дождевальные машины. Но в настоящее время эти земли оказались невостребованными, но в перспективе одновременно с осушением необходимо, конечно, и использование земель для орошения. Пожалуйста, дальше. Ну, для поддержки мелиорации земель соответствующее финансирование осуществляется как из федерального, так и из регионального бюджета. Существуют различные программы развития сельского хозяйства, вовлечение земель в сельхозоборот, которые финансируются из федерального бюджета. Есть также программа развития водохозяйственного комплекса Российской Федерации. Есть национальный проект экологии, включающий в себя проект сохранения уникальных водных объектов. Но данная программа реализуется под эгидой Министерства природных ресурсов и экологии Российской Федерации с участием нашего местного регионального министерства. Ну а что касается мелиоративных систем федеральной собственности, то этим занимается государственное федеральное бюджетное учреждение Калининград мелиоводхоз. Ну, полное название управление мелиорацией земель и сельскохозяйственного водоснабжения по Калининградской области. Ну, дальше, пожалуйста.
Владимир, пожалуйста, включите обратно микрофон. Да.
Все, включился, да?
Да, да.
Вот следующую, пожалуйста, слайд. Ну, что касается механизма субсидирования сельскохозяйственных производителей, то он включает в себя соответствующие субсидии, которые возмещают до 60% затрат, связанных с осуществлением культуртехнических работ на сельскохозяйственных землях. Также предусмотрено возмещение до 90% затрат, связанных с изысканием кислых почв. Но это связано с тем, что очень большая доля земель в зоне избыточного увлажнения относится к кислым почвам, и поэтому требуется проведение известкования. Кроме того, до 50% затрат предусматривается на возмещение стоимости работ по ремонту открытых мелиоративных каналов и закрытого дренажа. Но в части комплексной мелиорации с реконструкцией, техническим перевооружением осушительных систем и гидротехнических сооружений здесь предусматривается до 70%. Здесь речь идет уже непосредственно о подготовке земель для сельскохозяйственного использования, в то время как предыдущие затраты, они являются какой-то составляющей общей мелиорации, либо это ремонт закрытого дренажа, либо культуртехнические мероприятия. Ну, дальше, пожалуйста. Что касается эффективности поддержки выделенных средств, в том числе из областного федерального бюджета, то в 2020 году проведены мероприятия по ремонту мелиоративных каналов и закрытого дренажа общей протяженностью 870 километров. Ну, это позволило улучшить осушение земель на площади 11 070 гектаров и обеспечить защиту земель от подтопления и затопления на площади 3500 гектаров. Дальше, пожалуйста. Ну, опять же, что касается физических показателей выполненных работ в 2020 году, то это ремонт 443 километров межхозяйственных мелиоративных каналов, восстановление 174 километров дамб, реконструкция 8 осушительных насосных станций, известкование, соответственно, почв на площади 2,4 тысяч гектаров, а также культуртехнические мероприятия, известкование кислых почв на площади 2,2 тысяч гектаров и культуртехнические мероприятия на площади 2,4 тысяч гектаров. Ну и в целом это позволило создать условия для улучшения мелиоративного состояния осушенных земель на общей площади 60 тысяч гектаров. Дальше, пожалуйста. Ну, что касается выполняемых работ, которые завершаются в этом году, то проведены культуртехнические мероприятия на площади 670 гектарах, ремонт закрытого дренажа и каналов на площади 650 километров, выполнен ремонт, капитальный ремонт 3 насосных станций, проведена реконструкция 9 насосных станций и выполнено восстановление 178 километров водозащитных дамб. Ну, это позволит создать условия для улучшения мелиоративного состояния и интенсификации сельскохозяйственного производства, ввода дополнительных земель на общей площади 40 тысяч гектаров. Дальше, пожалуйста. Ну, благодаря осушению земель, вот с каждым годом создаются лучшие условия для производства сельскохозяйственной продукции. Но площадь осушенных земель превышает 257 300 гектаров, ну а общая площадь составляет, эти площади используются достаточно интенсивно под пашню, это площади посевов сельскохозяйственных культур, а общая площадь составляет 594 500 гектар. Ну и сельское хозяйство, оно является одним из важнейших направлений экономического развития региона. Ну, это связано с развитием, прежде всего, растениеводства, животноводства и увеличения объемов сельхозпродукции в целом. Ну, следующий, пожалуйста, слайд. Ну и что касается продуктивности сельскохозяйственных культур, то она достаточно высокая. И в 2021 году, в общем-то, регион, как и в 2020 году, в предыдущем году, он является одним из лидеров по урожайности сельхозкультур, ну и в частности по урожайности рапса, сои, зернобобовых культур. Ну и такие показатели, в общем-то, на процентов на 30 выше среднероссийских показателей. Ну а среди субъектов Северо-Западного федерального округа наш регион является лидером в валовом производстве сельхозпродукции. Но это, конечно, происходит благодаря тому, что область мелиорирована и ведется интенсивная работа по улучшению мелиоративного состояния земель, что позволяет ввести в оборот эти земли, а также использовать их более интенсивно, в частности, для выращивания зерновых культур, рапса и других культур. Ну, что касается результатов реализации проекта, связанного с использованием Wetlands, то это будет отдельный доклад представителя администрации Гурьевского муниципального района Калининградской области. Ну, что касается в целом области, то, безусловно, вот такие мероприятия, они могут быть проведены на достаточно большой площади земель, в том числе на польдерных землях, где, в общем-то, по своим характеристикам, высотному положению почвы, ряд земель по определению она не может использоваться интенсивно, то есть там достаточно наблюдаются высокие уровни грунтовых вод, каналы покрыты водой, в общем-то развивается бурная растительность каналов, и таким образом уже создаются условия для предотвращения излишнего сброса в водные объекты, в первую очередь Курский залив, Калининградский залив. И, ну, что касается вот конкретных предложений по внедрению ветландов, то это будет доклад соответствующий представителя администрации Гурьевского городского округа. Ну, у меня все.
Следующий слайд, пожалуйста. Добрый день. Я хочу поблагодарить представителя Калининград-Мелиоратхоз, заместителя директора Калининград-Мелиоратхоз Владимира Пунтусова за представленную презентацию. И хочу кратко сказать о результатах проекта WaterDrive на территории Гурьевского муниципалитета. Исходя из того, что вы сейчас услышали, понятно, что урожайность агрокультур находится в прямой зависимости от состояния мелиоративной системы региона. Но, как показали исследования, что основными источниками негативного воздействия на водную среду являются не только населенные пункты, но и промышленное развитие, а также сельское хозяйство. Особенности мелиорации нашего региона заключаются в том, что основными водоприемниками являются не непосредственно Балтийское море, а лагуны Курского и Вислинского залива. И значительным источником значительное поступление именно биогенов идет именно в эти водоемы. В рамках проекта WaterDrive большое внимание уделяется именно агроэкологическим методам.
Environmental measures in farming aimed at reducing eutrophication of these two water bodies. And one of the measures that we would like to implement in Guryev is a construction of artificial wetlands with surface runoff. That was the type of wetland that we chose for our municipality. North European experience shows that this measure is good for cleaning agricultural runoff from agriculture and reducing nutrient load. As part of, as an extension of our project, we conducted a research of the whole area of the Guryev municipality together with Kaliningrad-Meliorācijas. We chose 3 ditches, 2 of which are located in the Primorsk river basin, and they are part of the Koronian Lagoon catchment area, and 1 river basin is part of the Vistula Lagoon catchment area. Next slide, please. Taking into consideration our previous experience of trying to build a wetland in the Guryev river basin, this time we focused on researching a big area, of the 3 big catchment areas of these 3 ditches. We plan to make up a map of the potential sites for constructed wetlands and taking into consideration the experience of our Danish colleagues and diggers. Next slide, please. This is partially an illustration of what we have done, which ditches we have selected. This is one of those channels. The catchment area is over 400 hectares with 124 hectares of farmland. As soon as this channel is dense in its drainage network, it means that several small wetlands can be constructed in this area instead of having one big wetland. Next slide, please. The next channel is also within the catchment area of the Curonian Lagoon. It's part of the Kamyshova River Basin, and it also has a dense coverage of a drainage system. The catchment area is about over 300,000 hectares. With farmland 360 hectares, with farmland accounting for 340 hectares. And now we are specifying the locations where artificial wetlands can be placed in the future. Next slide, please. And finally, another ditch which we consider as a possible place of having constructed wetlands, and the Prahladno River flows into the Vistula Lagoon. The river is fairly big. It's the second largest in the category of among the rivers of the Kaliningrad region. It covers a big area, as you can see on the map, and in the top photo you can see the upper stream section and the lower stream section is in the bottom picture. The catchment area is 163.36 hectares and farmland accounts for 140 hectares. Next slide, please. I would like to draw a short conclusion by saying that application of agro-environmental measures, including constructed wetlands, as part of the drainage network, is a measure to improve the status of the farmland, which increases crop productivity, and it also reduces of the inflow of nutrients into the water bodies of the region. And I hope that after the WaterDrive project is over, we will develop new project ideas about constructed wetlands in Gurevsk municipality. I would like to say a few words about this project, thanks to which we learned a lot of new things about such agro-environmental measures as constructed wetlands, two-stage ditches, and now it will be very good to implement those measures in practice in Gurevsk municipality and wider in the Kaliningrad region. In the Gurevsk municipality, the flooded areas are extensive, meaning these measures could play an important role. A constructed wetland, on the one hand, purifies water from nutrients, coming from agriculture, and in the drought conditions, the water from the wetland can be used for irrigation of the fields. And the water is accumulated specifically in the wetland and is not drained into such water reservoirs as the Curonian and Vistula lagoons. Thank you very much for listening. I would like to thank our partners from Kaliningrad Meliorācijas, thanks to cooperation with whom we were able to conduct this kind of activity.
So thank you for your presentations so much, and now we will go on with the general discussion for a few minutes. We are a little late, but I hope you have the time to stay a little bit more. You can raise your hand if you want to ask something. There in the bottom of the bottom bar, you can there is a reactions, and there you can raise your hand. Or then you can also say it directly also if you don't find the hand there. Yes, and we have thought that we should discuss about this. What are the challenges in implementing drainage improvements in a technically and environmentally sustainable way? And what kind of research is needed in the future? And the need for improving and reconstruction drainage systems. But you can also ask the presentations what you want about. You can put your cameras on, at least the presenters would be good. Nice to see you.
I can see there are 2 raised hands. Staffan was first, so Staffan, please.
Yes, thank you very much, and thank you for interesting presentations. I have a question to our friends in Kaliningrad from the melioration. I think all countries around the Baltic Sea struggle with developing food production and protecting the environment at the same time. And what we can see in Sweden is that the environmental issues concerns the public more and more. And I wonder, what is the situation in Kaliningrad? Do you have the same kind of discussion, how to develop food production and at the same time protecting water quality, enhancing biodiversity? So I'm curious about that. Thank you very much.
Ну, что касается этого вопроса, то, конечно...
As far as this question is concerned, agriculture, farming in the region is one of the biggest polluters of the water bodies of the Curonian and Vistula lagoons. And this is related, firstly, to the intensification of agricultural production. But there are, at the same time, various activities, various measures which allow us to prevent increasing of pollution, regulating controlled drainage systems, for instance, and then which allows us to control the outflow of nutrients. There are also measures, activities related to the way fertilizer is applied. The main part of the region has the self-flow systems. And these are clay and subclay soils. And on the plow horizon line, the intensive nutrient leaching from fertilizer is happening, and if the timing of applying the mineral fertilizers if the timing is correct, this will reduce the leaching, but this means additional costs for farmers. But I agree that environmental pollution is a problem, the one related to agriculture, and this problem should be resolved using European experience of other countries, and this is one of the priorities for our region. As far as the specific outcomes are concerned, specific results, we conduct activities, environmental activities, but they are not of the overall scale yet in the existing farming conditions. Though we know that agriculture is a big polluter of environment, and we have been always aware of this problem. And certain attention was paid to resolving it, but it is still not fully resolved yet. I would also like to add a few words. about water bodies pollution by pork production companies. In Providence, for instance, which is a big pork producer in Kaliningrad, because they have problems with processing waste from pork production. And accumulation of animal husbandry waste is also a source of pollution. The waste could be composted, but this technique is not used in practice yet. And we are also talking about the slurry. The slurry as which can be a resource, but still is a waste. An authority that is involved in stopping the environmental polluters is agricultural inspection, which is a good instrument for stopping pollution to a certain extent.
Okay, thank you very much. Thank you.
Yes, thank you. And then Wendelin Wittmann has raised his hand. Please.
Thank you very much for the very interesting presentations. But I come back to that what Vladimir said and also to some contents of the presentations. So it was dealing much about constructed wetlands, about repairing something like the quality of the waters at the end of the pipe. So maybe it's also worth, or much more worth, to consider also to reduce nutrients input there where they come into the system. That means adapt fertilization and slurry utilization, as Vladimir also said before, and adapt it to the real needs, to the plants that are growing there. On mineral soils and for peatland soils, it should be avoided to drain them, so they must be revetted, and by that also nutrients input to the system can be reduced very much. So not only consider these end of pipe solutions, but go also in where it's possible to avoid inputs. Thank you very much.
Thank you. And do somebody else has something more to add, comments or questions? I can't see any hand more. So I think then we will conclude, and I will wish to thank very much all the presenters and participants, and hope you a very good day. And also in Friday, the WaterDrive will have a webinar about this revetting. So you can go on the website and look on that and do the registration if you are interested in that. Thank you so much. Bye.